Recording is on.
Okay, good morning, everyone. As I just said, so we are covering the graph problems. So we covered so many graph problems like BFS, DFS, detecting the cycles, and so you just said, Arvind, you said about the connected component is island, right? So,
Yes.
so here is how many islands have in this graph. Can you see my screen now?
Yeah, yeah. Yeah.
So the graph contains these are the elements A, B, C, D, E, F, G, H, I, J, K. So if this is the entire thing is a graph and there are four islands, right? So this is a one connected component. This is an island and E is an island. So F, G, H is another one and J, K is separate. That is also another one, right?
Totally
So
agree,
given a
right? FGHI will not be an island, right? Because F and I are not connected.
F and I are not connected, but those are you can read from F to I, right? So there is no direct connection, but still, there is a path from F to I. This is all connected. Let's say these are
Okay,
four stations. There is a road. There is a way from F to I. So I would think of that as a connected component. They're all
fine,
connected.
fine, fine.
It's a bidirectional. Yeah. So you can think of as a whole this whole graph. There are four islands or four connected components. That's the output returns four. So there are different ways of representing the graph. As you said, there is a matrix way. There is a way to represent using matrix, and I usually follow a different methodology like a tree. So basically, creating a node here and having adjacent to the list here. So this is another way of representing math, right? So I will contain a list of adjacent nodes. So for A, it will be B and C, right? For C, again, it will contain A and B as a adjacency list, correct?
Right.
So that's this is another way of representing. So this is the algorithm we practically like and we already covered in our last sessions. So get connected components. It just returns integer number. So we use hash table and we use the BFS algorithm. BFS always use Q, right? BFS
Yes.
use Q and DFS use tag. So using BFS, you can navigate all the nodes from a particular node. And once you completed node, we will take one more node from graph. So and we'll increment the count. So basically, you start from A and you cover all the nodes that can go from A. That means A, B, C, and you cannot go to D, A, or E anymore. So that's one component. So we'll increment the count there. We'll increment the count there, and then we'll go back to the graph and saying, hey, give me one more node. So if it gives B or C, it's already part of the table. So we don't consider navigating from B or C because it's already completed. You started from A and you already completed, B and C. So after that, it will give you the D. So D is completely new node, and from D you navigate to E, and there is no path from E. That so another component. That is another island. So I will increment one more time. That's how we do actually. So, and this is a Q, the BFS process. So we covered that. And the first problem is that. So, and the second problem we covered is detecting the cycle. How can we detect the cycle? And the third problem we covered is given a directed graph, find if we have a path between two nodes. So, is there any path between two nodes or not? I will give you two nodes. It just returns true or false. Can we
Okay.
reach or no? Right? So, let's say path is from 8 to 10. From 8 to 10, there is a path. We can go from 8 to 9 or 9 to 10. From 6 to 7, let's say it's a directed graph. Only 5 to 6, you cannot go from 6 to 5. So, in that situation, do we have a path of 7 to 6? Even 5 to 6, you cannot. This is a directed graph. There is no way from 7 to 5. So, in that situation, you cannot reach from 7 to 6. So how can we find that? We covered in the last session. The recording as well, you can look into that. So this is the path. Each path is with the basically we can have two nodes, start node and end node. So So how can we figure out that? So we covered in our last session. Uh, and the next one we covered is the given an undirected, given a directed weighted graph, find a path, find and pick the shortest path. Now, the before algorithm is just like it will say whether there is a path or not. Okay, it will say true or false. Is there any path? Is there any line between two distance? Yes, true or false. But this one will find and also print those paths. This is the one actually find, print shortest path between two nodes covered in the last section. This is unweighted, right? So unweighted means weighted unweighted graphs. Arvind,
Yes, yes, yes. The
yeah.
edges will
What
have
is
weights, right?
exactly? It's kind of you can think of weight as the distance between those two
Yeah,
nodes
it,
or
it
a
is like a
weight or
weightage given to the particular path's cost. We can say how much
yeah,
cost
you
would be
can think
incurred
of
for
as a
between two
cost.
vertices. Yeah, something like that.
Exactly. If you are thinking as train stations, it could be a cost, or it could be miles, number of miles to reach
Yeah.
from one station to another station. So yeah, so that
It's
that
like
that's what we covered
the
last week.
scenario like going to source to destination with minimum cost. Like it can be done using a minimum span only,
Exactly,
right?
exactly. That's the one. Yeah, minimum span. Okay. So this problem is unweighted. This the last week we found. This is for unweighted graph. This particular algorithm is unweighted. Let's say shortest distance from A and F, right? If you want to go from A and F, so there are multiple paths. You can go from A, C, B, F, A, F, right? So AGF is easy, just only A and F, right? So since it is unweighted, we don't know the path. We can think of a weight of every no every edge is one, right? Let's say A to G is 1
Yes.
mile, and C to F is also 1 mile. So in that situation, if you go from AC to F, it will be 3 miles, right? Whereas AGF is just 2 miles. So you can in the unweighted, it's easy to find, but in the weighted, it is tough. So last week we discussed about this one. So how can we find shortest path in an unweighted graph? So Aranya, should I repeat this one, or do you? Is it? Yeah, did you get a chance to review the code last week?
No, Suresh, not
Yeah.
yet.
So we discussed this one. So I can quickly go through this problem again to understand better. So because it is complex and also it really helps to understand the other problem, right? So the one which we are going to discuss is weighted. So let's see shortest. Yeah. So I use C. I'm Microsoft technology, and most of my algorithms are in C sharp. Uh, I don't know. Are you comfortable with it? I think you're from Microsoft, right? Microsoft technology, right? Arvind?
Actually, I worked on C sharp. I'm very much comfortable.
Nice,
But
nice.
yeah, I'm going forward.
Yeah,
I'm planning to practice in Python because I find it much more
Python.
easier. Yeah.
Nice, nice. Yeah, I did not get a chance to learn Python, but yeah, it doesn't matter. This particular this kind of algorithms, any language is almost
Yeah.
same, right? There is not.
The logic should
Yeah.
be the remain same.
Only the little bit of uh, what is that the change is little bit of the syntax will change. Yeah, little bit of syntax change there. So so I'm opening here. Yeah, it's still opening there. So in the meantime we can yeah. Okay, in the meantime we can discuss here. So basically display shortest path, right? So how can we display shortest path between two nodes, start node and a node? So we decided to have different ways of solving the problem. So one way is to having two hash tables. We want to take two hash tables, one for keeping the depth of each hash, depth of each path as we are going. And another one is to keep track of previous node for each node. So basically, we will store the depth. So if I go from A to G, G to F, right? So it's like 1 plus 1. So if I go from A, C, B, F, so it will be 1 and 2 and 3, right? So we will store the depth of each node. So how far we are going, right? So we'll maintain path tables for that, and we will go with the BFS. So BFS is the best way. That was it. So we'll put it in a queue, and then we will initially will say start node equals 0, and then hash path start node equals 1. So there are the hash path is for storing previous nodes. Basically, you want to print the path, right? In order to print the path, you need to store the path of the node. That's what we are saying, the hash path, and hash depth will store the depth of the node. So we'll go through the queue, and we'll go to the next node. We'll take the first node, and we'll go to the all the adjacent nodes, and we will check whether you already visited that. If you did not visit that node, we'll put it in the hash path. We'll put it in the hash path, and we'll also put it in the queue. And the hash path is basically, hey, you came to this, and here is the parent node. Sorry, this is the child node, and this is the parent. So we want to store that path. Otherwise, we cannot print the path, right? And another thing here is you need to add the depth. Okay, you are visiting this node by adding depth. Basically, depth of the parent node. Okay, let's say you are from B to F, but in order to reach B, you already traveled 2 miles. From A to B is 1 mile, and B to A is another mile. So you can think of as a depth equal to 2. You will mark the depth for each node. Now, basically depth of B, come on, depth of B is 2, 2 plus 1. In order to reach from A to F, it will be 1, 2, 3. But by the time you reach from, you would have reached from A to G and G to F. So that before you reach F. So depth of F will be actually 2. Start from BFS, right? When you start from BFS, travel all the three nodes. You put all C and C in the queue, and then after processing the C, you process the G, and when you process the G, you will have to process the F. So that's how it is like. So we are getting the depth. Okay. So I clearly like I detailedly explained in this class. So finally, once we have all the nodes covered, right? So we will figure out whether we found that path or not. Let's say the node is completely in a separate island. If the node is separate island, we will never be able to reach. There is no connection. But if it is part of this path, that means it is the same island. It is the same island, then you will be able to reach. And here is the shortest path. So printing the path requires the hash table, the hash path. It will print out the nodes because you're already storing the parent node, right? It will print in the recursive way. So let me run this problem. Come on. So speak really slow. Okay, if I run without debugging. So the shortest path from A to F has to print ACF, even though we have other paths like AC, EF, EF, AC, DEF, there are different paths, right? But what is the shortest? AGF. So that's what I'm expecting. Is it still running? Oh, output is still running. No, let me run again. it's still building. So it's all about the unweighted graph, right? In unweighted graph, we are thinking there is a value for one for each edge, right? So we are just simply incrementing one for each edge. But if it is a weighted graph, there will be a weight, there will be a value for each graph. Then how can we figure out? That is the main problem. So that's what the Dijkstra algorithm is to figure out the minimal path. You need to every time, let's say A to C is five miles, A to G is 8 miles. You will decide which to go, which is the best way. So which is the shortest way. Basically, you will find the shortest and then visit the shortest node, and you will be able to reach your goal or not. So that's how it is. Why it is not coming? So it's still building. No, no. Maybe eventually this will be really fast. Yeah. See,
Okay.
shortest path, shortest path
Can
from
you hear
A to
some
G.
background noise, Suresh? What is it? Some
Oh,
disturbing
you're
noise.
hearing some background noise?
Yeah, yeah.
Maybe from is it from Aravind? Maybe Aravind, can you mute? I think there will be some little bit of noise.
Oh, I don't think. Okay, anyway.
Yeah.
Yeah,
Now it's
okay.
now it's clear, right?
I
Yeah.
think it's fan.
Yeah. Little bit. Yeah. But
Sorry, the
anyway, if
fan is
you feel
on.
free to unmute anytime.
Yeah, yeah, I will
Yeah.
mute and
If you
then
have
once
any
it's
questions.
on.
Yeah. So you understand the problem here, right? So the shortest path is AGF. So A to G and G to F because every path is same weight. So there is no, differences between any path. You can took any path, but because every edge has the same value one. We are just incrementing plus one. But in case of weighted graph, this is not the case, right? So this is the for weighted graph. There are a lot of algorithms and like a lot of description here. I will go with one of those. I think I found here Dijkstra's algorithm. Yeah, in the Geeks for Geeks, they already clearly explain. So I will send this link as well. So how to find the shortest path algorithm? Okay, so this is a kind of greedy algorithm. They said so. Let's say you want to find a path from a shortest path from 0 to all the nodes, or maybe you can think of as 0 to 4. Let's say what is the shortest path from 0 to 4, or it's really big. Maybe you can think shortest path from 0 to 8. What is the shortest path from 0 to 8? So you can calculate 4, right? 0 to 1 is 4, and 1 to 2 is 8. So 4 plus 8 is 12. 12 plus 2 is 14, right? If you go from this way, 0 to 8 is 0 to 7 is 8, 7 to 8 is 7. So that means like it is like 15, right? So 14 is better than 15, even though just one node, right? So even though just you are visiting only one station, 0 to 7 and 7 to 8. But the problem here is it's a cost wise, it's more cost. Maybe let's say this is the shortest path, but the cost, these are the costs. If you think of this as a cost, you are paying more. But if you go this route, even though there are multiple stations here, you are paying less. Okay, if you think of as a cost. So the shortest path, let's say shortest means the distance. If you're thinking as a distance wise, even though only one station, but the longest distance, you need to have 8 miles here and then 7 miles, it is 15 miles. But rather than if you go this way, just 14 miles, right? If you think of as the shortest path, this is a shortest path. So how can we figure that out? This is all the algorithm is all about how to write the algorithm, how to write the problem, the solution to display this path. If I give you the question, hey, print the path from 0 to 8, shortest path. It has to print 0, 1, 2, 8. It should not print 0, 7, 8. So how can we do that?
Uh, at first, we can check whether there is a path between our source and destination,
Okay.
and we can source and destination, and how many paths are there.
Yeah.
Uh,
Different paths. How many paths? Okay.
okay, so we can calculate the distance of each path from the source to destination and store it in an array or map or a set.
Yeah.
and find the greatest of them,
Greatest or
or
smallest? We need smallest,
smallest of
right?
them. Yeah.
Yeah. So this is exactly way to do. Basically, you need to find. Uh, but this is a one way. Whatever you said is good, but the problem here is you are doing multiple iterations. So first one is finding whether there is a path, and second one is what are all the different paths. If you want to reach 8, right? The one path is 0, 1, 2, 8, 0, 1, 7, 8, 0, 7, 8. There could be another paths as well. So you are finding all the paths, and along with the path you are also calculating how much cost or how much distance you traveled, right? So that is also a good way. It's not a bad solution, but you are exploring all the paths all the time, right? And finally you are finding what is the smallest, and for the smallest what are the nodes. So the solution what you said is correct, but it takes a lot of the execution time and also a lot of memory, because you are storing all the paths, right?
Yes,
So
but
0, 1,
without
2,
knowing
8,
all the
these are
paths, how
paths.
will we come up with the smallest distance, Suresh?
Exactly. That is the main logic here. So basically, what we need to do is, let me try to explain. This is very complex, and let me try my best to explain. So what we need to do is we will do the same BFS algorithm as we discussed. We will do only one traversal. We will start from zero, and we will travel each node. What we are going to do is, for each node we will assign the value. Basically, not value. What is that? Um, uh, he said we need to assign a value. So let's say you want to reach. You are starting from 0 to 1. In order to reach 1, right? You will assign, hey, you travel from 0 to 1 and the cost is 4. Cost, or let's say distance is 4. You will assign 4 to this particular node. Okay. Now let's say you did not go this path. Let's say you went this path. You started from 0 to 7 and 7 to 1. Let's assume that. So what happens is 0 to 7 is 8 miles, and 7 to 1 is 11 miles. Totally, in order to go from 0 to 7, 7 to 1, how many miles? 19 miles, right? Because 8 is here. So value of 7 is, in order to reach 7, you need to travel 8 miles. Okay. Value of 7 is 8. And then from 7 to 1, 11. So, you need to add this 8 plus 11. What happens? 19. So the value of 1 is 19. Correct? That is one path. One way to reach 1 is like 0 to 7, 7 to 1. You can reach 1 that way. But later you figured out, hey, there is a direct path. There is a direct way from 0 to 1, which is just 4 miles. So 4 miles is better or 19 miles is better? Which one you prefer? We want shortest.
For
4
my
miles, right? So you travel this way. Basically, you are traveling in one way. So let's say it's a BFS or DFS, whatever the algorithm, you already traveled from 0 to 7, 7 to 1, and you are marking each node with the value. So for 7, the value is 8. For 1, the value is 19. But later you figured out this one, which is 4. So the value of 4 is like, this value is smaller than the existing value. The existing value at this node is 19. 19 is way bigger and 4 is small. So you erase that 19 and put 4 there, because you found a smallest path, which is better path than the path you already traveled. So now what happens is the value of 1 becomes 4. Now from 1 you will go to different paths. Okay. So now from 1 to 2, the what is the value for 2? What will be the value that you need to 2?
12.
12, exactly, because the value of 1 is 4. You don't need to look at the graph here, because you already assigned the value. If I scroll here, I can show you. See this one. See, I already assigned value 4 there, and I assigned the value 8 there. So now I'm assigning a value for 2. What is the value for 2? Is basically value of 1 plus the value of the arc or value of the edge, which is 8. So 4 plus 8, 12. Okay. So now what happens here is you will do the same thing for 7. From 7 it's 8, and 7 to 8 could be 15. If you travel 8 through this way, it will be 15. Now later you travel from this way, 12 plus 2, 14. So then you update the value there, because smaller value. So that's how we will assign the smallest distances to every node. Okay. So look at this here. So see the 15. See, they updated 15 here because 0 to 7 is 8 and 7 to 15 is how much distance? Is 7. So 7 to 8 is 7. So total 15 there. So you will put 15 at the beginning, but later it will be updated with 14. Look at here. So you figured out smallest number. So because you can reach 0 to 8 within 14 miles. So that's how it is. Basically, we will maintain a hash table or a hash set. Yeah, a hash table actually. Hash table. The key is the value of the node, and the value is the basically the width or the distance you travel from the beginning node to that node. Okay. Let's say from 0 to 5. So the value for 5 will be assigned multiple times, but finally the smallest value will be there at the end of the algorithm. You will see how to reach from 0 to 5 within a smallest distance. What is the smallest distance? Will be 8 plus 1 plus 2, right, which is 11. If you go any other route, let's say 4 plus 8 is 12, 12 plus 4 is 16. So it will be 16 if you go from 0 to 1, 2 to and 5. So there could be another way, 0 to 1, 2, 8, 6, 5. You can reach multiple ways, but always it is costing more. This is the best route. Okay. So basically we will assign the value at one point, and again you will keep on assigning or changing the value if you find a better path. That way you will figure out what is the smallest from this node. So look at this algorithm. Yeah, look. So pick the vertex with the minimum distance value and not already included. So basically what we do is we will pick the minimum distance and then we'll go from there. So let's say how to start this algorithm. So this algorithm starts from 0. This is the starting node. So we will navigate to the smallest nearest station or the nearest node. Nearest means we will check what is the smallest. If you have only two connections here, right, one connection is to 1, another connection to 7, and what is the smallest? This is the smallest, right? So you will pick the smallest and then travel to that node. That is the best way. So rather than picking 8 and then here, so we will pick the 4. We will pick the 4 is smallest. So we'll pick the 1 and we will travel to 1. Okay. Then from 1, again, we'll do the same algorithm. What is the smallest? Okay. We'll pick the smallest one and then we will travel. So that's what they are saying here. We don't want to visit the node which we already visited. That is another thing there. So is it clear?
Which I have a question.
Yeah.
Uh,
Right.
yeah. Uh, Previously, in the original diagram, we are having a connection from 1 to 7, right?
We had a connection from 1 to 7. Oh, here, yeah, 1 to 7,
Yeah,
11,
1
11
to
miles.
7.
Yeah,
Yeah. Now, in the new picture we are creating using this algorithm, we are completely ignoring it and there is no connection there. Is it
yeah.
so? Because the
The
cost is
reason
huge.
exactly cost is huge. So we are always thinking that we are always finding the path from 0. Okay. So what is
Okay.
the algorithm here says we need to find shortest path from 0 node to all the nodes. So
Okay.
So 0 to 1 is this is smallest, shortest node, and 0 to 7, this is the shortest path. There is no point of going from 0 to 1 and 1 to 7.
Okay.
Okay.
So there will,
So
if what if there will be a problem arise from 1 to 7? So if according to this picture, the second picture, the later picture we developed, it cost us
yeah,
12, which is more than already we have. So for every source and destination, we have to construct this map. That's what the idea is.
exactly.
Okay.
Yeah. The idea is to update the values of each node to represent the smallest path from 0. Okay. So in order to reach 1 from 0, just 4 miles. Okay. In order to reach 7 from 0, there are two paths, 0 to 1, 1 to 7, which cost around 15 miles, right? Which is like 15 miles, 4 plus 11. Another one is 8, just 8 miles. So we will update with the smallest one. So that's why the value of 7 is 8. Got it?
Yes.
Yeah. So Arvind, are you following or any questions?
Yeah, Suresh, I'm following. I will try to assimilate, and if I have any questions, right, I will
Yeah.
ask you.
Sure. Sure. Yeah. Awesome. So this is the algorithm. Basically, we will figure out shortest path, and then we'll assign the shortest value to each node. So algorithm says like this: create a set, shortest path tree set that keeps the track of vertices included in the shortest path, whose sum that the distance from the source is calculated and finalized. Initially, it is empty. So he's just explaining how to do this. So assign the distance value to all vertices in the input path. So initialize, so this is assignment and initializing with all as zeros. And while visiting any node, if it is not visited already, so we'll pick the vertex which is not there, and then we will assign the distance value. So update the distance value of adjacent vertex of you. To update distance value, iterate through all the adjacent vertices. So this is a clear explanation how to do this. So basically, algorithm says we need to start from here, and we need to visit every node, and then we're going to update. So what are the ways to visit? The visiting is basically we'll find the shortest path, shortest node basically. So let me show you. It a little complex here, but I will try to explain. See if I can make it easy. Okay, where is it? Really, I think it's, yeah. So one is, before we jump into the algorithm, how can we define this? Until now, we discussed about only we discussed about the graph node, which doesn't have any value to the vertex, right? So we already discussed about how to represent a node, how to represent the edge. So we will connect these two things using adjacency list. There are different ways again. So the way I define here is using the arc. So let me go to the node data structure. Here is a node. So every node contains the name, which is a value. It could be a, b, or string value. And okay, it also contains the arcs. What is arc? It's a kind of adjacency list only. I'm maintaining as a list of arcs. Each arc contains two things: what is the parent node, what is the child node, and what is the weight. Basically, an arc means an edge. So if you look at this is an arc. Okay, what is the parent node? 0 is parent node, and 1 is child node. You can think of parent child. So that means you can go from 0 to 1 with the value of 4. And at the same time, this is a undirected graph or bidirectional graph. That means you can go from 1 to 0, 0 to 1. You can consider 1 as the parent and 0 as the child. Let's say these are the city names. 1 is one city, 0 is another city. Like people can travel from 1 to 0 with 4 miles, and 0 to with 4 miles. There is no difference, right? This is a road. If you think of as a road with 4 miles, 4 miles distance between these two cities, anyone can go from 1 to 0, 0 to 1. So this arc represents two things: the parent and the child and the weight. That those are the three things: parent, what is the parent node, and what is the child node, and what is the weight of that. So that is the arc. So now if I want to have this connection between 0 to 1 with 4 miles, how many arcs I need? I need two arcs, because this is a one way and this is another way. If you are thinking as a highway, right? They don't just build one thing, they will build two other way as well, right? The vehicles will go from 0 to 1, go in one road, and from 1 to 0 another road. There is a divider between those two, right? We should not go in a opposite way. There will be separate lanes from one direction, right, from 0 to 1, and there is a separate lane to travel the vehicles from 1 to 0. So how many roads there? Actually there are two roads, two separate roads, correct? Do you agree? That means two separate arcs, of course the same distance, because it's a side by side roads, right? One is one direction, another road is on the another direction. Got it?
Yes, yes.
So establish that arcs. So how can we establish that arc is? That is what we add arc method. So basically here is a node, here is a node, the node name is 0, and 0 has how many arcs? So this particular 0, the node 0 has how many arcs? 2, right? One arc from 0 to 1, another arc from 0 to 7. For the first arc 4 miles, for the second arc 0 to 7 8 miles. So this particular list, for the node 0, this particular list has two elements. Okay, so that's what we do. Add arc. Basically, add arc is a method that will add this child node and with the weight 0. So we will check if the arc is already there. We don't want to add the arc. If it is not there, we will add the arc. New arc parent equal to this. That means this is the node you are adding to this node, which is 0. And the child is, this is a child which you are going to pass with the weight W. Okay. So here I am adding a reverse link as well, reverse arc from the child to the parent. This is the extra method I'm doing. If you are constructing a route, if you are paving a road from 0 to 1, immediately I am creating another arc from 1 to 0 as well. I don't want to, say, hey, create one more arc from 1 to 0. If I am saying create arc from 0 to 1, internally I am creating another arc from 1 to 0. That's what this method does. It's a little complex. That's what I'm doing here. So adding a reverse link or reverse arc from child to this parent. So if arc doesn't exist, add the arc. Here the parent is a child. Now child is this object and the weight is the same weight. We don't want to change the weight, right? The distance from 0 to 1 is 4 and 1 to 0 is also 4. The same weight, but it is a different object that we are going to add to the child object. So it is a little bit complex. So but anyway, what I'm saying here is basically for this node we are adding a child node here with a weight 0, with a weight W. This is how to maintain the arc. So there will different ways. If you use matrix, there is a different way. If you use adjacency list, different way. This is a kind of adjacency list, but instead of storing the adjacency nodes, we are storing in terms of arcs, adjacency arcs. Okay. So the first we need to understand the what is the representation, how to define this. So that's what it is. So let's say the node 0, right? So let's look at the node 0. I am adding two arcs from node 0 to node n1 and from node 0 to n7. N1, how much? What is the distance? 4 miles. N7, 8 miles. That's exactly what we have, right? N1, 4 miles. N7, 8 miles. So that I'm creating that graph. N1 to N2, 8 miles. N1 to N7, 11 miles. So the whole exact the same graph what we looked in the website. I created that the graph here. Okay. Finally, this is a graph is always simply a list of nodes. There is no complexity of creating graph. Until now you created the nodes, until now you created the nodes and their connections and their arcs. Finally you are putting everything in the graph 0 to 8. Okay. Now find shortest distance of each node from starting node and 0 using Dijkstra's algorithm. So what are we doing? We are finding the shortest distance of each node from the source. What is the source? 0. It's not like you are finding between two nodes. You can still do that. So but here we are finding shortest node from each node, like from 0 to 1, 4 miles, 0 to 4, it will give you the answer. How many miles, what is the shortest distance? It could be like 9 plus 2, which is like 11, and 11 plus 20 is 10, which is 21 here. But if you go this way, it could be smaller, right? We don't know. Which is 12 here. 12 plus 7 is 19, huh? And then 19 plus 9, right? So this could be longer, this could be the easiest path. So it will find all the paths, and it will tell you in order to reach 4 from 0 what is the distance. It will tell you all the different shortest distances of each node from 0. So this is actually algorithm. So it is little tricky algorithm. We can go through that. So but anyway, so if you understand the algorithm, maybe we can go through this full details of each and every line next week. So in the meantime, I can send you code. You can also look at the code and how this works, you know. So this is exactly this works the exactly the same way that I just explained. So we will go through each path, and we'll assign the value to each node. And if you find a greater value, or if you find a smaller value, we will update the value. That's what it does here actually. So if you are able to reach a child node with the less weight, then it is than its previous weight, update its weight. So that's what the crucial part of this is. That is the main part here. We are updating the weights there. So basically, as I said, we can take the two dictionaries. One is the node distances. As I said, for every node, we are going to assign a value, right? So we are putting in a dictionary. Dictionary, you can think of it as a hash set. No, it's a hash table, right? I don't know about in Python. What is the terminology in Python?
It's
Hash
same.
table.
There is explicit
Table.
sir. We can. It's a
Yeah,
inbuilt, like we can just dict for that.
exactly. So we will take that hash table node and two value. Basically, it's exactly like what we are doing here. For every node, we are assigning a value. In order to assign a value, we'll put it in a hash set. The key is the node, and the value is the integer value, which is basically the distance from 0. So, and we are putting in a hash table, which is hash set, actually hash set or hash table, processed elements. We are putting in a processed elements. We don't want to process an element which we already processed before. Okay. So node distances. Let's look at the first starting algorithm. So in order to node start 0, right? If you are starting at node 0, this is start node, and the distance is 0. If you are going from 0 to 0, is just 0. So node, like let's say this is 0, so we are assigning 0 value there. So there is no if this is 0 value, 0 miles from the same distance to the starting point. So that's the starting, and then we'll see. So processed elements count not equal to graph count. Basically, processed elements are 0. You did not add anything. So we will loop this until you process every element of the graph. If the graph has 100 elements, we will process until the elements in the hash table becomes 100. So that's what we do. And the next one is, this is what I'm talking about. We need to traverse. It's not a BFS, it's not a DFS. This is a different traversal. We at every point we will pick the nearest node. What is the nearest node? Okay, at nearest unvisited node. So basically, you are at this location. Where are we right now? We are actually it will figure out. So basically, node distances and processed elements. Okay, this particular method will give you the next node to process. See, this is the beauty of this one. You know the BFS, we'll put it in a queue. You know the DFS, we'll put it in a stack. But here we will do a different traversal. Give me the nearest node. Okay, it will give you the nearest node. This method will give you the nearest node, and then we will put it in the processed element. We will process that element. So how this method will give you the nearest node? This is the logic here. So you have a dictionary of nodes, and you have a processed elements. So what we do is we'll take a minimum value as a maximum value of integer, and now what we do is we will traverse to the node distances, Okay, we will iterate to the node distances. Basically, we will iterate to the nodes and we'll figure out what is the minimum value. Okay, so that's what we do here. So if you find a minimum element, then that will be the nearest node. So what I'm saying here is, what is the first step here? So I think it is better if I write in a whiteboard. Yeah. So here is the processed elements, right? We will add the node distances. Let me open the whiteboarding. If I can open this. So this is the tool I use. So what is the graph we have? Here is the graph, right? Come on, I want to go to the top. Oh, okay. Here is the graph. So 0, 1, 7. So we have. Let me put it there. What I do is I will put it here for a bit. My system is really slow today. Come on. Okay. Okay, I'm going to write it down now. So we have 0, and here is 1. This is 0, and here is 7, right? And we have 2. This is 6. We have 8. So we have other nodes. So anyway, so I don't want to write everything at this point. So let's see. So now what we do is,
Is it disconnected?
I think so. Suresh, Suresh,
I think
Suresh.
so.
Session is not. It's never happened. I have messaged him. Let him come back. Uh,
Sure,
Arvind,
sure.
Arvind,
Hello.
how we are planning to once a week or twice a week? How we are planning to meet?
Plan. Okay. Uh, how like what is your free time, ma'am? Like how can we? That's what I'm also
Um,
thinking.
okay, actually, I can adjust myself because I'm working from home.
Hello.
Yeah, since I'm working from home, uh, I can
Actually,
adjust. So,
I'm in hybrid mode. We have 3 days of office, 2 days of work from home.
are you able to hear me?
Hello.
So, okay. What about Tuesdays and Thursdays?
Tuesdays and Thursdays, huh? Okay.
Yes. At what time will you be available?
Timing. Can we fix 9 o'clock? Same like this. 9 o'clock is fine.
Yeah, it's fine.
I'm
Mm,
okay.
Okay. What are your actually? Do you have any? Uh,
Hello.
oh, Suresh, what?
Yeah, Ravind. Hey, Karanya, can you hear me?
Yeah, I can hear you. What?
Yeah, actually, my system hung here. It's not in a not responding state. Something happened. Maybe I need to restart my box thing. Maybe, but anyway, so the algorithm is a little bit complex. I will send you the code. You look at the code and try to understand. Next week, I will do the whiteboarding. So how we
Okay.
are going to solve it. So
Okay.
basically, taking it's a two hash tables. Basically, one hash table, and there are two hash tables we need to take, and we'll do the full whiteboarding next week. But anyway, that's the whole purpose of the algorithm, is to figure out the paths between starting node and rest of the nodes, the shortest path. Okay.
Okay. So
So
for every source and destination, we have to use this algorithm to find the
yeah,
short.
this algorithm is to find shortest path from a particular node to all rest of the nodes in the graph.
Okay, to rest all of the nodes in the graph.
Exactly. This will tell you what is the shortest from zero to all the nodes. So the algorithm will tell you the shortest nodes. Basically, if you want to see, you can think of as a example, right? You want to put a station, and you want to see what is the distance of each location. Let's say from Mumbai, what is the shortest path from Mumbai to Hyderabad, Mumbai to Delhi, Mumbai to Vizag, Mumbai to Chennai. So it will give you shortest path from a particular node to rest of the nodes. From there, you can select any node. If somebody say, "Hey, give me the shortest path from Mumbai to Delhi," you already have that knowledge, right? You already have that information in your system. You can simply say, "Hey, this is the value." Simply, you will surface that value to the user. So that's how the main advantage of this. This is a for weighted graphs, right? So for weighted graph, this is the best algorithm to use to figure out.
Suresh, will they ask such complex algorithm during interviews? This seems to be composed of so many functions and
Yeah, Karan, actually, this is one of the much asked kind of a question. So it won't be very straightforward. Like we have this kind of logic in many of our scenario based, like for this kind of tech companies. It's much sort.
okay, sir. Okay, Suresh, will be next week.
Yeah, let's meet next week. My system is not working properly, so I will Arvind, please join next week as well. We will do the whiteboarding, and we'll explore this algorithm very in detail. Okay.
Definitely, Suresh.
Okay, Suresh.
Okay, then cool. Yeah, we'll meet you next week. Okay. Yeah. Have a nice week. Yeah. Bye.
Thanks for that. Hello.
Arvind, 9 p.m. is it okay for you?
I'm not hearing you.
No.
Hello.
Okay, we shall chat. It is not so audible. I'll chat you in Discord.
Okay, fine, fine. Bye bye.